The anatomy of a black hole. The recent image of Sagittarius A*, the supermassive black hole at the heart of the Milky Way by the Event Horizon Telescope, has brought these tremendously massive spacetime events to the forefront of the public consciousness again. Yet, images like this, and that taken of the supermassive black hole at the heart of Messier 87, can only go so deep. How are black holes born? The presence of a stellar mass black hole indicates a star that has reached the end of its main sequence, hydrogen burning, life, and lost its battle against gravitational collapse. The lives of stars are marked by a constant balancing act between the inward force of their own gravity and the outward forces generated by nuclear fusion. As this collapse proceeds, stars that have enough mass above what is called the Chandrasekhar limit can trigger further fusion reactions, creating heavier elements and halting the collapse. This process repeats for these stars, which are at least 1.4 times the mass of the Sun, until only the quantum properties of a dense fluid of neutrons protect the dead star against further collapse. This results in a stellar remnant called a neutron star. But some stars are massive enough or can grab enough material from a companion star to exceed even this limit. That leads to the complete gravitational collapse of the star and the creation of what is termed a stellar mass black hole. A tale of two singularities, the structure of a black hole interiors. To understand what is going on in black holes, it's necessary to touch on the crowning achievement of the physicist Albert Einstein, the geometric theory of gravity, better known as general relativity. The most common analogy used to picture this is the placement of balls of increasing mass on a stretched rubber sheet, with a bowling ball creating a more considerable dent than a tennis ball or a marble. What general relativity also says is that in a region of extreme density, two singularities arise, points at which mathematical calculations fall to zero or move to infinity, always bad news for physicists. One of these singularities is a coordinate singularity, meaning physicists can eliminate it with a clever choice of coordinate schemes. The other, the true singularity, can't be handled in this way, meaning it currently represents a point in the universe at which all physical laws break down. Unsurprisingly, these two singularities are of vital importance to the structure of black holes. The coordinate singularity represents what is known as the event horizon of a black hole. This is the surface that bounds these massive spacetime events and is as deep as we can possibly see into them. This is because the event horizon is the point at which the gravitational influence of the black hole is so great that not even light moves fast enough to escape. The structure of black hole exteriors. While the interiors of black holes may seem almost disturbingly simple, where these spacetime events get really exciting is in their immediate environments, especially true where a central black hole is feeding. More accurately called accretion, this happens when black holes are surrounded by a disk of gas and dust, understandably called an accretion disk. The material in an accretion disk is flattened out and prevented from falling straight into the black hole by its angular momentum. This results in it gradually falling to the surface of the black hole, a process that powers a wealth of energetic phenomena. The particles in an accretion disk are sped up to tremendous speeds by the tremendous gravity of the black hole, often approaching that of light. These turbulent conditions result in them being heated to superhot temperatures estimated to be as high as up to 10 million degrees and emitting powerful X-rays and gamma rays.